So this practice session on combinatorics is devoted to basically those who are having doubts in a lot of the fundamental concepts like fundamental counting principles and I'd say binary sequencing or stars and bars or gapping method and some other things, basic things. So let's look at the very first thing, which is nothing else but product rule. What is product rule? Product rule is a rule that applies when there is more than one variable. Product rules applies when there is more than one variable. Product rule is applicable in case of more than one variable involved in determining the final outcome. More than one variable involved, they are interlinked or they have an interdependency, then only we can apply the product rule. Like there is a very basic example. Consider the example of buying coffee. It sells 4 varieties and 3 sizes. When you are choosing your coffee, you need to choose both variety and size. Don't go figuring out how many choices you have in total. So this is just an example, an illustration of just forgot about this. No need. So we are in a coffee shop. This is the size of the coffee and these are the varieties. This is size, this is varieties. There are 4 different varieties, 3 different sizes. So the total number of possibilities are 12. Now this is how we are solving it, counting without actually even counting, because size and varieties are interdependent. But now in case we do not know, so how we will solve it? We will simply count. Just see, this is a variety, this is a size, it is having 3 different options. Similarly for this we are having again 3 3 3 3 3 3. Similarly 3 into 4. We can just say that this rule is valid. This was quite unnecessary illustration. Again, the class looks like a cafe. The class looks like a cafe. So whatever. So now we are in a sweet shop. This is a sweet shop and these are the varieties of donuts and these are the varieties of bagels. Now we can choose any one sweet. Any one sweet. It's not like that the case of dependency. So any one sweet, we can choose this, any of this. There are 1, 2, 3, 4, 5 options, or we can choose anyone from here. 1, 2, 3. There are 3 options. We will add them up. Just look at this. We are adding this. So here we are applying some rule because these and these are not dependent on each other. They are independent variables. They are independent variables. So this was the very basic philosophy, and I hope that everyone, this is some rule. Now we'll see a new rule Just so this is called Shepherd's law. Why this is called Shepherd's law? Actually, in easy language, I would say that this is division principle, division rule. But there's a fancy name to this known as Shepherd's law. Now let's see the philosophy behind this Shepherd's law. One way to count the sheep is to count the legs and divide by 4. So we are dividing, just focus. Provided each sheep has exactly 4 legs. In mathematical term over. In mathematical term over. Overcounting by a uniform multiplicative factor. We will see the example. Overcounting by uniform multiplicative factor can be corrected by dividing this factor. This is also interesting and easy rule. Let's look at this. For example, we're having in how many ways can the letters of the word cinema be arranged so that the order of vowels do not change? Order of vowel do not change. What are the vowels here? I, E, and A are the vowels. And if we are supposed to arrange the entire letter cinema without any kind of restrictions, in how many ways we can do this? There are 6 different letters, 6 factorial ways. Now this 6 factorial way includes the different arrangement of IEA, but there is only one unique arrangement of IEA, which is this IEA only, because vowels are in the same order, but they can be arranged in 3 factorial ways. And in the total number of ways, we can just simply divide it by 3 factorial ways to get the unique arrangement of IEA, which will even give us the answer. 3 factorial divided by 6 factorial is nothing else but 120. That is the division principle. When we are doing this 6 factorial, we are also including the different arrangements of IEA. There are 6 possible arrangements of IEA, 3 factorial arrangements of IEA, which is equal to 6. When we are arranging the cinema in 6 factorial ways, we are also including the different arrangement of IEA. But it is given that vowels, it is given in the question that vowels are arranged so that their order do not change. So we cannot have this 3 factorial different ways of arranging this IEA. So we can simply divide it, and that is division principle. That is the benefit advantage of division principle. Consider three boxes, each containing balls numbered 1 to 12. Suppose one ball is randomly drawn from each of the boxes. Let us denote the level of the ball drawn from the ith box as Ni equals to I. 1, 2, 3. Then the number of ways such that the balls can be chosen such that N1 greater than N2. Consider three boxes each containing balls numbered 1 to 12. Okay, very fine. Suppose one ball is randomly drawn from each of the boxes. Let us note the level of the ball drawn from the ith box is Ni. Ni equals to I is meaningless here. What is Ni equals to I? Now this is correct. So we are having what is given in the question, that we are having three boxes in which 12 different balls are there leveled 1 to 12. And the number of ways balls can be chosen such that, please do not focus here. Please do not focus here. This is quite distracting. Then the number of ways such that the balls can be chosen such that N1 greater than N2 greater than N3. Suppose we are choosing a ball numbered 8. Here we need to choose a ball number 7, and here we can choose number 4. N1 greater than N2 greater than N3, because this is the first box, this is the second box, this is the third box, and it is given that N1 greater than N2 greater than N3. Quite easy at all. Now, the number of ways such that the balls can be chosen. Just look at this. These are the three boxes. How many balls are there in the first box? 12. Now one ball is chosen. One ball is chosen among the 12. We can't choose that ball. We can't choose that ball. So for here we are having 11 different options. And for here we are having 10 different options. Now we will simply multiply them. But there is a problem. When we're doing this is not satisfied. Just say we are getting an arrangement 754. Well, this is satisfied. This is a satisfied expression. Let us rearrange this. We can get 574. We can get 475. Similarly, how many different arrangements are there? How many different possibilities are there? 3 factorial. And we need only one possibility among these 3 possibilities, that is this 754. So we will divide this simply by 3 factorial, division principle. And this makes the problem easy. So this was known as Shepard's rule. Now we'll see an interesting thing. Gap method, stars and bars method, binary sequencing. What is the method? There are so many names. Let us do not remember any of these names because these are different names, different people can give this strategy different name. Let us not remember any of this name. Look at this example. Just look at this example. This is very important one. In how many ways 6 boys and 4 girls can sit in a row so that no two girls are together? This is the classical example of this gap method. There are 6 boys. Say boy, 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 boy. 1, 2, 3, 4, 5, 6. And no two girls are together means that what? We can place the girls anywhere in between the boys. In this scenario, the girls will not be together. So how many places are there for the girls? 7 places. And how many girls are there? 4. This is 7, choose 4. Now the girls are different, so they can be arranged among themselves in 4 factorial ways. And the boys are also different. They are not same. So they can also be arranged in 6 factorial ways, and this is the answer. So this was gap method. This was gap method. When two, this is very interesting also. When two different person thinks anything, two different things can't be together. Just focus on this statement. Whenever we will get this statement, can't be together, that means that they are sitting in between the gaps of some other things. This is the only possibility that they cannot be together, which will give us our answer. And there is no other method to solve this kind of problem. They can't be together. Just simply remember, they have to sit in between the gaps, and that's why it's called gap method. Why it's called binary sequencing? I do not want to turn over. Just these are just simply symbols and nothing else. Now let us see. I guess there was a question from Burnell method. Yes. In how many ways can 6 boys and 4 girls sit in a row so that no boy is in between a girl? In how many ways can 6 boys and 4 girls sit in a row so that no boy is in between 2 girls? That means what? Girls are together. Say concrete block. 4 girls are sitting together. They are the 4 girls sitting together. In between them, no one can come. Now, what we will do, we will consider this as a single unit. We will consider this as a single unit. So, this is a single unit, and there are 6 boys. So, total number of things are what? 7. 7 factorial. There are 7 factorial ways of arranging the single unit of girls and boys. But now, an interesting thing is that the girls can be arranged among themselves in 4 factorial ways. Among themselves in 4 factorial ways, we will simply multiply this by 4 factorial, and this is our answer. This is our answer. Let's move forward. Prove Beger's formula. We have already discussed Beger's formula. And why we're discussing this proof of Beger's formula? Because I got to know from some students that this they're having doubts in the proof of this Beger's formula using their binary sequencing method. They're not understanding. Simply, they're not understanding. Find the number of non-negative solution of x1, x2, x3, xr. R and n are natural number. So this is nothing else. This is nothing else. But I'm just giving a hint. Use permutation with repetitions. Use permutation with repetitions. You'll get it. So now let us prove it. So how we will prove this? Nothing difficult at all. Let us consider this x1, x2, x3, xr as boxes. This is the first box, this is second box, this is third box, this is the rth box. Say these boxes are separated by the stars. So how many stars are there? Just look at this. Suppose, just for a moment, let us forget this xr part. So for x1, x2 and x3, how many plus signs are there? Only 2. For 3 different boxes, we are having 2 stars. For r boxes, we will have r stars. How many stars are there? R minus 1. Yes. R minus 1 stars are there. Now, this n is what? This n can simply visualized as n can be simply visualized as 1 plus 1 plus 1 plus 1 plus 1 up to n times, up to n times. So it's not visible. This n can simply visualized as 1 plus 1 plus 1 up to n times. It's now pretty clear. What is n? So what are the number of non-negative solution? What are the number of non-negative solution? Just see a small example. Say we have x1 plus x2 plus x3 equals to 5, which is nothing else but 1 plus 1 plus 1 plus 1 plus 1. 5 ones are there. Just look at this. This is a box having 2 ones. Means that x1 equals to 2. Means that x1 equals to 2. This is a box having no 1. Means that x2 equals to 0. And x3 is a box having 3 ones. Means x3 equals to 3. So we are just putting these ones in the boxes. We are just putting these ones in the boxes. How many different ways are there to put this 1 in the boxes? How many different ways are there to put this 1 in the boxes? Are simply number of non-negative solutions. Are simply number of non-negative solutions. This is what known as Beger's method. This is what known as Beger's method. How many ways are there to put these numbers in the boxes? How many ways are there? Suppose there are 4 ones in the second box, 2, here 1, here also 3 ones are there. I'm just supposing. We can change the arrangement. Now, who will change the arrangement? Just see here the transformation that I'm going to perform. Let me put the star here. Just see. I have put this star here, and what happened? This one is now here. You can see there are 3 ones, there are 3 ones, there are 3 ones. So in the first box we are having, in the first box we are having 3 1. So here the value of x1 has changed to 3, and this will give us a new, I would say, ordered pair. This is not pair, can be triplet, quadruplet, or anything of solution. Am I correct? So what are the total number of solutions? The total number of solutions are just simply the total number of arrangement of the stars and these ones. Replace a star, get a new arrangement, you will get a new solution. Replace a star, get a new arrangement, you will get a new solution. Now here let me show you that this x1 x2 can be 0 also, because this is given non-negative, and this will also be satisfied. Just look at this example. 111 star, 111 star, 11 star, so on. Star, say 1. Now how they can be 0? This is x1, this is x2. Suppose x2 equals to 0, how the stars arrangement will represent it? Simply look at this. Let me put the star here. Let me put the star here. 111 star, star, 111. Nothing is there, star is here. 11 star, so on, star 1. This is x1. This empty space is x2. This is x3. Here x2 is having no 1, means it is 0. Means it is 0. So this arrangement of stars and ones are giving us the number of solutions. This is clearly visualized now. There are no more doubts. How many arrangements are there? We will use permutation with repetition. We will use permutation with repetition. We are having r minus 1 stars and n number of ones. So total number of thing is n plus r minus 1. N plus r minus 1. These are the total number of factorial, total number of arrangement divided by the repetition r minus 1 n factorial. If we clearly visualize it, we will get that this is simply n plus r minus 1 choose r minus 1. This was the visualization part. This was the visualization part. And this is Baker's formula. This is Baker's formula. Hence, we have proved Baker's formula. From the miscellaneous practice, the questions were already given, so we're not going to discuss all the questions. I'll discuss 4 questions. So the first question, there are unlimited number of boxes of 5 different color. How many arrangement of at most 7 boxes? This question. There are unlimited number of boxes of 5 different color. How many arrangement of at most 7 boxes in a row can be made by using them? Just think about this question. There are unlimited number of boxes of 5 different colors. How many arrangements of at most 7 boxes? Just try to solve those who haven't solved. Question number 3, 4, 5 also, 7, 7 I am not going to solve. I just give you a hint. 11, 12. These are the questions not visible. Just look at the question number 3, question number 4, question 5, then question 7 that I am not going to solve, question 11 and question 12. So now let's start. There are unlimited number of boxes of 5 different colors. How many arrangement of at most 7 boxes in a row can be made by using them? This was quite an easy question. The number of balls are unlimited. This is the first box, this is second box, this is third box, this is fifth, this is sixth, this is seventh. For the first box, we are having 4 options. Sorry. There are unlimited number of boxes of 5 different colors. 5 options. For the next also we are having 5. For the next we are having 5, 5 and 5. This was the case when the number of boxes were 7. This is the case when number of boxes are 7, but this is given at most 7. At most 7. That means that the number of boxes can be less than 7 also. When it is at most 7, this is 5 to the power 7. That is correct. But when it is less than 7, this is 5 to the power 6. Say number of boxes are 6. Then we have 5 to the power 5. So on. When the number of boxes is 1, we will have 5 different options. So this is a geometric progression. I guess the basic lecture of sequence and series has been completed, so we should be able to solve this geometric progression. This is 5 times 5 to the power 7 minus 1 into 5 minus 1, which is equals to 5 by 4 into 5 to the power 7 minus 1. And this is the answer. At most 7. See, while in the MCQ kind of examination, there will be options where the answer is 5 to the power 7. And there will be this kind of options also. So there, those who will not read this at most 7, they are definitely going to give a wrong answer. That's why question 3 was important. Now, this is again an easy question. In how many ways P dissimilar blue books and Q dissimilar red books can be arranged in a bookshelf such that no 2 red books appear together, assuming that P greater than Q? This is again a question of gap method. No 2 books are together. As I said, whenever we will see this statement, no 2 are together, that means this is a question of gap method. And this is also given P greater than Q. P blue books, Q red books are there. There are Q red books In between the red books, we are going to place the blue books. So these are the spaces for the blue books. These are the spaces for the blue books. So how many spaces for blue books are there? How many spaces are there? Sorry. In how many ways P dissimilar blue books? Okay. P blue books. P blue. Q red books are there. In between the red book, what are the number of spaces available? Q plus 1. Q plus 1 is the number of spaces available. And in between the space, we need to select P number of spaces for arranging the blue books. This is P plus 1. Sorry, Q plus 1. This is Q plus 1. Choose P. So these are the positions which have been selected. But the Q books and P books, blue books and red books are also dissimilar, so their arrangement matters. Multiplied by P factorial times Q factorial. And this is our answer. So, in a class, 10 boys and 11 girls, the teacher wants to, oh, this question is not required. Easy question. A supervisor goes to Delhi to supervise 3 different projects A, B, C. A supervisor goes to Delhi to supervise 3 different projects ABC. He needs to visit every project for exactly 2 days, and he cannot visit 2 different projects on the same day. As well as he cannot make consecutive visits to any project. See, no 2 visits can be together. Language is changed. No 2 visits can be together. In how many ways he can visit the projects on a business trip of 14 days? So here with this session, we will complete the topic of this gap method. We have also shown one example of bundle method. These are easy things, a regular thing, not for the non-routine part, but okay. Well, we need to study the routine part first before studying the non-routine. A supervisor goes to Delhi to supervise 3 different projects ABC. He needs to visit every project for exactly 2 days. He cannot visit 2 different projects on the... So total number of visits he needs to make are what? Total number of visits? 6 out of 14 days. How many days he is not visiting? 8 days he is not visiting. And no 2 visits can be consecutive. No 2 visits can be consecutive. That means these are the non-visiting days. Say, let me denote them by stars. And the visits are made in between these spaces. In between these spaces. He has to make a total of 2 into 3, 6 visits. 6 visits. So the number of days he did not need to make any visits out of his 14-day business trip is 8. So these are the possibilities where he can visit, as no 2 visits can be together or consecutive. The stars includes these non-visiting days, 8 days. How many options are there? There are total of 9 spaces, if you can see. 9 choose 6. But the problem is what? 9 choose 6, okay, it's fine. 9 choose 6 is fine. But this is not the answer. This is not the answer. Just emphasize on the fact that A, B, C are 3 different places, and he is making a total of 6 visits. He is making a total of 6 visits, and the 6 visits can be arranged in 6 factorial ways. Out of these 2 visits are these AA, BB, CC. So this is permutation with repetition. The different places he is visiting. 2 factorial, 2 factorial, 2 factorial. We will multiply this by this, we'll get our answer, and this is the final answer. That's why this question was interesting. Now I guess nobody is having any kind of problem with this stars and bars method. Last few questions. In a particular programming language, in a particular programming language, a variable name can consist of a sequence of 1 to 6 alphanumeric characters A, B, C, Z. So how many alphabets are there? 26 alphabets are there. And how many numbers are there? 10 numbers are there. Beginning with a letter, beginning with a letter, beginning with a letter. Find the total number of valid variable names. Find the total number of valid variable names. This is a damn easy question compared to the previous question. The first position, language variable name can consist of 1 to 6 alphanumeric characters. This is again the question of that geometric progression idea. 1, 2, 3, 4, 5, 6. This is the largest possible name. At most 6. The name can be made up of at most 6 characters, made up of 2 characters, made up of 1 characters, made up of 3 characters, made up of 4 characters, so on. It can be made up of 5 characters. We will see the case of the first case. Beginning with a letter, the first letter always is having the alphabets. There are 26 different alphabets, and then it can be alphabet or a number, that doesn't matter. So 26 alphabets are there, 10 numbers are there, a total is 36. From then onwards it's 36, 36, 36, 36, 36. Now simplification will be quite easy for us. This is again a geometric progression. At most, remember this, at most 6. 26 into 36 to the power 1, 2, 3, 4, 5. 5 plus 26 into 36 to the power 4, so on. 26, 26 common, 36 to the power 5 plus 36 to the power 4, so on. 1, 26 into. And now you can do this. The first term is 1. The first term is 1. And we have 36 to the power. This is easy thing. 6 like this, minus 1 by 36 minus 1. This is our answer. Sum of geometric progression. That's not important. Two similar questions. Last question. It's easy questions. That's why at the very beginning, this is practice session level 0. Level 0 for those who are having difficulty in the basic. Because if your basics are not clear, you won't be able to solve questions. In how many ways can 10% sit in a row of 24 fixed seats such that no 2%? Again a question on the stars and bars method. Stars and bars or gap method, whatever. No 2% take consecutive seat. Answer is also given. I guess this was a homework question, but let's solve it. In how many ways 10% sit in a row of 24 seats? 10% are sitting. Total of 24 seats are there. 14 seats are vacant seat. So in between the vacant seat, people are sitting. So there are 15 possibilities of sitting. These are the 14 vacant seats denoted by the stars. Here I can sit. So that no persons, in between the persons, at least one vacant seat will be there. Always. At least or more than. That is not the issue. 15 seats are there. 15 possible seats are there. Seating arrangement, I would say. 15 possible seating arrangements are there. In between the vacant seats. And I need to choose 10 seats out of there. 15 choose 10 and the 10 persons now can be arranged in 10 factorial ways. This was again an easy question based on stars and bars method, and that's what we need to discuss.